So this is expert Fonda and we are watching on YouTube. So let's continue to understand today Leetcode question that we have is 1319. So question is saying number of operations to make a network connected. Okay, so look like from the graph. So now understand there are n computers which is from 0 to n-1 connected by Ethernet cable and connections forming a network where connections of I you can say is AI and BI, means A and B. So each connection is connected with each other with two computer AI and BI. Any computer can be reached any other computer directly or indirectly through the network, right? So you are given an initial computer network that is called connections. You can extract each extract cable between two directly connected computers, right? Okay, and then place them between any pair of connected disconnected computer to make them directly connected. Now we have to understand the minimum number of times you need to do this to in order to make all the connection completed, right? And if it is not possible, we have to return -1. Okay, so let's understand example 1, in which it is saying that we have given what n is the number of connection, n equal to 4, right? Sorry, number of, you can say, computer, right? And we have given what connections, that is we have given like this. Okay, so connection is saying 0 is connected with what 1, 0 is connected with 1, you can say. Okay, and then it is saying 0 is connected with 2 also. Okay, so this is connected with 1 and 2, like this you can say. And now it is saying that 1 is connected with 2. Okay, like this. Okay, so each one is connected, only 3 is not connected, right? So what we have to do, we have to return the minimum number of times you need to do this in order to make all the connection, all the computer connected, right? All the connected, how many connections is required. So if we will do one connection, right? So we are going what, why we are going from here to here, right? So if I'll connect either from here, right, either from here or either from here, right? So there only one connection is required to connect all the computer, correct? So we say because we can connect from each other, right? So what we can do, we have the connection right here, so we can connect like this. First we have 0 computer, it is connected with 1. So now 0 is connected with 2 also, right? What we can do, we'll connect 1 from 3. So minimum connection is required is 1, right? So either anyway you will go, you will get one connection to make it all computer connected. And if we'll talk about this one, so it is saying that we will remove the cable between computer 1 and 2, and then we will place between 1 and 3. Okay, so we are removing these connections from here and we are making between 1 and 3. Okay, so we have to read one more time the statement. I think I have missed something. So there are n computer that is connected between that is number between 0 to n-1 connected by the Ethernet cable connections and forming network where connections of I is A and B, represented connection with computer A, between computer A and B, and any computer can reach any other computer directly and indirectly through the network. So you are given initial computer network connections and you can extract certain cables between two directly connected computers, so place them between any pair of this one. Okay, so you have to extract, right? It is saying that you can extract the cable and you can put, that's why it is what it is saying, we are extracting from here and then we are putting into here, right? And between two directly computer and place them between any pair of disconnected computer to make them correctly. Yeah, that given. Okay, I got it. Now understand another example 2 in which we will see this one. Okay, so similarly we have connected 0 to 1 it is connected, 0 to 2 is connected, 0 to 3 is connected, and 1 to 2 is connected. Okay, now 4 and 5 is not connected, correct? So what we have to do, we will how many connections we have to do? So for this one we can remove this connection, not required, and then connection not required. So if I'll remove this connection, right, so what we will do, we will continue this connection like 0 to 1 and 1 to 3 and 0 to 2. What when I disconnect this connection, so I can put here, and means this connection is not here now, and if I'll disconnect this one, so this connection will come to between here, right? So it will look like this one, correct? So minimum 2 connection is required to extract and add. Similarly, if we have 6 0 1 0 2 0 3 and 1 2, so there are no enough cables to implement. Why? Let's suppose we have given it is saying 0 is connected with 1, and 0 is connected with 2, and 0 is connected with 3, and 1 is connected with 2, right? Like this. So we have like this. Okay, so we require at least if I'll remove this one, right? So we can make this like 0 1 2 and 3. Now it will look like this one, right? And if this one is also connected, let's suppose, but if I'll remove this one and will make like this one, so it is still one is remaining here. Okay, so not enough cable we have here. Now understand the constants, right? So n we have viewed is greater than equal to 1 and less than equal to 10 to the power 5. So what we will do, we have to make connections dot length is greater than 1 and minimum is n minus n into n minus 1 by 2, right? And 10 to the power 5, which is minimum, that will be our length. So connections we have dot length is equal to 2, and b we have given greater than equal to 0, and n a not equal to b, and no repeated connections would be there. No repeated connection we have here, and that's why we are considering the last one as this one. Okay, and no two computers are connected by more than one cable. Understood? So this question is very important, because see, this question has been asking all the top companies. You can say Amazon, Facebook, Apple, Google, Microsoft, right? All top companies are asking this question. So this is very important question, we can say, and you should do the practice. So what we'll do, there is multiple approach, right, in which we can do by you can say depth first search, or you can say width first search, right? You can implement this one. Either you can do also by the union find, right? So approaches are very clear, right? Either you can use you can say DFS, BFS, or union find. Okay, so in the last video study questions that I have already gone through the DFS, right? So if you're not aware with the DFS I have gone through, you can use the that one. Okay, or if you are aware with DFS and BFS, right, it's fine, you can use a union search, and you can implement this one. Okay, so it's also very fine. You can also implement this one, right? So what I'll do today, I'll try to implement all these three, and I'll put here on the all the videos, right? So first of all, I'll go through you can say depth first search, in which we will implement the implementation, right? So we are given an undirected graph, right, and we have n nodes, you can say, right? So to do that, what we have to do, actually we have given an undirected graph, you can say, and for that with n nodes you have given, right? So which are referred as computer from 1 to n computers we have given, right? And this is all are connected with some connections, right? And so we have seen that this is our connection array, and any edge that is that connects two nodes can be placed and you can say replaced, right? So between any two disconnected node, right? It was saying if it is connected, two nodes are connected, right? So this can be replaced and placed in any disconnected nodes, correct? And our task is to return the minimum number of edges, right, that must be placed in order to connect the entire graph, right? So if there is no way to connect the entire graph, we must return -1, right? So what is our task? So our task is to find the minimum you can say number of edges that need to be placed in order to must be replaced in order to, you can say, connect the entire graph, correct? That we have already seen. So let's go to the depth first search, and we'll try to implement this one. Okay, so the depth first search, if you remember, right, so let's suppose we have given a graph that we have is Let's suppose I'm taking here as a 0, then I'll take 2, then we have what, let's suppose we have not 3, we have 4 and 5. Okay, and these are connected like this. Okay, each one is connected with each other, even this one is also connected. Okay, so we will let's suppose we will break this one, right? We will break this one, and we will break these you can say 2 edges from this component and use them to connect with the other component. Okay, so other components are, we have 3, we have 1 and 6. Okay, so 1 and 6 are connected. Okay, so if we will break this one, so we can connect this one, right? So what we will do after breaking this one, right? After breaking this one, let me go here. What I'll do, I am breaking this one. Okay, now I have break. So what I will do, I will connect with some other. So I'm going to connect with this one. Correct. After this, let me change the color. Yeah, now what we have another set right here, this one. So if I'll remove this one, right? So let me remove this one. So let's suppose now we have removed this one. So now what we can do, we can connect this one with other one, right? So what we have 0 is connected with 2, 0 is connected with 5, like this. So I'll connect with this one. Okay, now you can see 2 and 4 is not connected now. It is not fully connected correctly. Okay, so what we have to do, we will remove this one, right, and we'll connect this one. Okay, so let me erase this one now. Okay, so now as you can see, now this is our answer. Okay, so as you can see, how many you can say we have used the you can say edges, right? We have used here. Okay, we have used how many connection, right? So understand our intuition. What is our intuition we have here is let me take the pen. Okay, and I'll change my color. Okay, so a connected graph with our you can say some edges we have given is a tree, right? So if we have fewest edge with a connected graph, right, is a tree with n-1 edges, right? So if we have n-1 edges connecting with all its nodes, right, so that is called our tree, right? Because all are not connected, right? So if in order for a graph n nodes to be connected, the graph must have at least what, n-1 edges, right? This feature you already knows, right? So if you are following my videos, you already know that if we have n-1 edges, right, so at least n-1 edges should be there to be a graph should be connected, right? So you can write here, if a graph is connected, for a graph is connected, there should be at least n-1 edges, right? So this is our concept. So or otherwise it is possible to connect the graph, right? Now understand, is it impossible, right, to connect a graph that has fewer than n-1 edges, right? So it is impossible actually. Yes, it is impossible to connect a graph that has fewer than n-1 edges, because this is our rule, right? Otherwise it is always possible to connect the graph. The very simple answer. Okay, now we will return -1 if the number of edges in the graph, as you can say, is less than n-1, right? If n-1 edges we have, right, if we have n-1 edges, then what we will do, we will return in our answer that -1 as answer, right? Because if we will if our edges, if the number of edges in our graph, let's suppose this is our graph, is what we have n-1 edges, right, and it is not connected, it is less than, you can say less than n-1, right? So we can say if the number of edges in the graph is less than n minus 1, so when if it is less than n minus 1, not less than, yeah, if it is less than n minus 1, then what we will do? Edges, then we will return minus 1. You got it, right? Otherwise we can connect the entire graph if we have at least n minus 1 edges, right? What are you saying? We can connect the entire graph, right? And if I have at least n minus 1 edges, let's say our graph has you can say different component, right? Like we have earlier seen, right? And then we have connected this one. Okay, so if we have at least n minus 1 edges, then some component must have extra edges, right? That we have seen, right? And that edges we will replace with these edges to connect other component that we have seen, right? We have a replay, we have edges, right? So what we have used that edges to make the all component together, right? So how many edges do we need to replace this one, right? So imagine each connected component is simplified in just a single node, right? So now what we will do to connect the simplified graph, we know we need a minimum you can say the given component that you have, right? So if we have component, total component we have C, right? So we just will do minus 1, right? So that is our edges. Understood what I'm saying? Let's just assume that, right? If you have you can say if you have a graph, right? And graph has what? C different component, that is directly component, right? And if have at least n minus 1 edges, correct? So then some component, right, must have extra edges that we have seen, right? And we would replace these you can say edges to connect all the component, right? Now you will understand, so how many edges does we need to replace, right? So how many edges do we need to replace? Imagine that each connected component is simplified to just a single node, right? And now we should understand to connect the simplified graph, right? What we will do, we know a minimum number of C minus 1 edges is required, right? So our answers will be what? C minus 1, right? So we can imagine C minus 1 edges connecting to the original component. You will understand, no, don't worry. So you have seen this example, right? So if there are at least n minus 1 edges, the solution of the solution is what? Number of connected component must minus 1. If number of component we have given, like let's see, right, just we will do C minus 1 we will do, right? So if there are at least n minus 1 edges, right, the solution is number of number of connected component minus 1 will the answer. Otherwise we will return minus 1 that we have already seen. I think you have understood. So this example will fulfill our requirement, right? So what we will do, we'll try to implement this one, right? And whenever we find our extra edges, right, so those extra edges we will use to replace to make the connected entire graph, right? So I'll suggest let's go to the coding section, and then we'll try to implement this one, so it will become a little easy to say everything. Okay, so let's go. Now we are here, and we are going to implement this one, right? So first of all, we have given these connections, right, and number of nodes we have also given, right? So what I'll do here, first of all, we'll check the number of component, right? So we'll check if this is, you can say, base case, you can say, right? Now we have connections, right? We'll do connection dot there is a function length, right? So we'll from the length function, right, we'll check if it is less than n minus what 1 to check the connected component, right? If we have less than n minus 1, then what we will do, we'll do minus 1, sorry, minus 1 will do. If not connected, if not fully connected, if not fully connected, then we will return -1 if that is the case. Now we should understand, right? We'll similarly we'll know that we will create adjacent node, and then we will traverse that all the nodes, right? So to do that, we know that we will create one hash map, or you can say map, and this map will contain our first integers, right? Integer, and others will be our list of integers, other nodes, right? That is also integer. This is a node and list of node. Okay, you understood? Node and list of node. Then we will take our adjacent you can say nodes, right? And it is equal to what? We'll take a new hash map, and it will look like this. Now we have our hash map. Now what we will do, we will initialize our adjacent nodes, right? To do that, what we have to do, we have the connections we have. So on the connection, what we have to, we'll get 1D array of connections. So for each connection, we'll get our connection, right? From each connection, what we will do, we'll get our we will try to initialize our adjacency, right? So now we have adjacency nodes, right? ADJ adjacency nodes we have, right? On this one, what we will do, we'll take compute or if present, right? So we'll take compute if present, if absent, and then we'll take two things. The first, we have connection at what? 0, and at connection at 0, we'll have some item, and that item is nothing but we have some node, right? And this node have some you can say list of, I think we'll take list of array list, and you can define the type also, integer, right? Once this is done, we'll define our add, and on the add we'll pass our connection at 1. So each node is connected with other node, right? And that's all we have. This should work. Now similarly, we'll take for another node, right? Vice versa we have to do. So this is become 0, and this will become 1, correct? So each node is connected with each other. So node, let's suppose if this is node 0, right? So what I'll say, node, this is our node A. Node A, where we have connections we have. So at connection at, you can say 0, what we have node A. And similarly at connection at what we can say at 1, we have connection node B. So if node A is connected with a list of another node, right? So we know that node A is connected with node B, right? That's why we are adding like this one. Okay, so all the connection will go, and we'll have how node A is connected with either node A, B, C, D, that it will come. It will store into the, you can say, adjacent map, right? Like this. So there will be node A, and all the node will come into as a list here, right? And that's why we are taking like this one. I think you understood. Okay, so after this, what we should do, we will check, we have to find actually our component, right? How many component we have, right? And we'll try to find this one. Okay, so what I'll take, we'll take our integer, and I'll say number of, you can say, component, right? Number of component will take, right? So components, yeah. So I'll take number of component, and this will start from what? 0. Now we'll take you can say visited node, right? So we'll take our visited nodes, and these visited nodes will take what? Will store in new boolean. So we have to define the boolean type, right? and so that and so I'll go here and define its type. Okay, now we have visited nodes, so we'll check, we'll try to go to all the nodes. I'll start from I equal to 0, and we have given number of nodes, right? So I'll take n and I plus plus. From 0 to n minus you can say n minus 1, you can say, we will go, all the nodes will go, and first of all we'll check all the nodes, right? If we have not visited, right, if this node is not visited, right, then what we will do, we should increment our number of connected components, right? So we have our number of connected components, I'll do plus plus, right, and we will do the DFS of this node, right? So I'll do we'll create one DFS utility method, DFS utility method, and this method will contain what, the first will pass our the node, and then adjacency you can say list, and then I will pass we will pass our visited node. Now we will create you can say this DFS utility method, like, okay, later, but this will update our number of connected component, and will return here, right? This is our function returning something. So what we will do, we will return number of connected component, you can say, and minus 1. If this is less than minus 1, right, if number of component minus 1 will do. If it is returning, right, means what, we have our connected components, right? I think this is we have. So just we have to create the DFS utility method as earlier we used to do. So first of all I'll create this DFS method now, and then I'll try to check. This method is not returning anything, so I'll take void as its type, and this DFS utility method I is nothing but our node, right? So I'll take int node, and adjacent node, you know that it is a map, so I'll take from here to here. And for the visited nodes, what I'll take from here to here. Okay, so visited node will take what you can say a list of you can say it will contain all the list, right, in the array form, right? So we have not defined like this, so we should define like this also. Okay, so it will work. It's good to we have seen. Now we'll put onto the visited node, right, like this one. Now the method structure is ready. Now what we will do, we'll try to implement this one, and we'll find the DFS method. So first of all we should check if the node is already visited, right? We should make it visit. So first of all, the node that we have, make it as a visited, as a true, you can say true. And if this node is you can say now we have marked, so we'll check onto you can say if not urgency we have, if in on the urgency node, if it is if it contains, right, we'll take contains key, and we'll pass our node, and we'll check. If it is not onto the here, so we'll return, will not do anything. And if we have, right, if we don't have the urgency node, we'll return. If we have already on the urgency, then what we will do, we'll say urgency node dot get is a method, and we'll pass our node. So this if urgency have data, right, then what we will do, we'll check our all neighbor, right? So I'll get all the neighbors of our node, and what we'll do, we'll check if this, if its node this is our neighbor node, right? If the neighbor node is visited, right? So to do that, we have our visited. So on the visited we'll check NEI neighbor node, and we'll make the loop, and not loop, you will make the body, and we'll make we'll first mark this visited node of I. You can say this neighbor is true. Now we have marked this one, and then we'll do the DFS as we have done earlier, right? We are doing recursive thing. So we'll pass first NEI adjacency, and the visited node will remain same because I have not changed the name, so it will remain same. So what I'll do, first of all, I'll start from the here. So first of all, we are going to do what, this is our DFS method, right? DFS approach. So in the DFS approach, what we'll do, first of all, we'll check our you can say it is connected or not connected. If it is not fully connected, then we will return -1. Other than if it is fully connected, number of nodes is the length less than length. And then what we'll do here, we'll take urgency nodes, and then on the all the connections, right? What we'll do, first of all, we'll mark these connections onto adjacent nodes, so that our urgency map will be initialized, right? And we'll take a number of component, and we'll make a visited node, so that on all the nodes we'll go and we'll check if it is visited. If it is not visited, then will number of component will increase, and we'll do the DFS, right? And finally we'll return number of component -1, C -1. If it is C -1, it will be true. We'll have our number of component. Now what we will do here, we'll take this DFS method, and this DFS method will do what? First of all, we will mark the visited node, and if this visited node is not over the urgency map, it means we have to traverse this one, its children, and we'll check if urgency we have, then we'll get our neighbor nodes. We'll check the neighbor nodes is on visited or not. If not visited, then we will mark it as visited, and we'll do recursive call for the this neighbor node, and all the neighbor node we will traverse like this, right? So that is called DFS, because we will get our first parent node, and from the parent node we'll go to all its neighbor, right? We will traverse all its children. That's why it is saying that it's DFS method. Okay, so I think you are understood. If you have any doubt in this video, right, so you can ping me in the comment box. So let's compile this problem, this code. It's working. Let's submit this one. So it's working fine for me. Okay, now what we'll understand, we'll understand this one. You can say, let's go to here, understand the time complexity. Okay, so time complexity, and if we'll talk about the space complexity, both will remain same, because if there is a O of n plus E, you can say, right? So E is a, you can say, number of nodes we have, right? And E is the total edges we have, right? Because say we are going to initialize the adjacency list that will take O of n times, right? O of n time will take to visit the array, and to initialize the adjacency will take O of E time, right? Here where we have here, and we are initializing here, so it will take O of E, right? It will take what? O of E time, right? And after that, what we are doing, we are visiting the visited array, right? Here we are going to the visited array, right? So it will take O of n, and that's why we are taking this one. And in both places we are taking spaces also, like we are taking array and visited node, so it will take space complexity will also remain same. So that's all we have for today video. Thank you for watching this video. For more videos, please subscribe our channel, so we will get more videos like this. Thank you guys.